we look at singly reinforced concrete section. Under bending. So let's draw the diagram. We have a section of this nature. And it has an overall depth. Let's draw the neutral axis line. Then with an overall depth, of H, an effective depth of D. Here we'll consider also another imaginary line passing here. We draw the stress diagram or the strain diagram first. So I have a strain diagram. Use this to wipe off part of this. So we also go ahead to draw the stress block diagram. I have this. So I have something of this nature. So here we term this as our neutral axis depth, which is X. Use overall height of the section. And this is the breadth of the section. And this B as the breadth of the section. Then this is concrete strain. Here we'll have this steel strain. And here we'll have depth of the stress block. We'll proceed with the labeling. This is B, this is H, this is D, effective depth, this is overall height, this is X, depth of the neutral axis, while this is the neutral axis, then this is EST, this is ESC, which is equal to 0.0035. Then this is length of our stress block. Then this as 0.45 FCU, and this is where we have our force in concrete, and this is the force in steel, as our FS, force in steel as our FS, force in concrete is FCC. So here we have FCC. So this is our section. First diagram here is our section. Then this one is our strain, which is B, strain. Then C is our stress diagram. So here we have Z. Consider depth from this portion to this portion. We'll use a straight line, make it neat. from this point to this point, make it lighter. So this point to this point as our Z, and here the Z is equal to lever arm factor multiplied by the effective depth, LAD. So next thing we'll consider is S is equal to 0.9x here. So for a singly reinforced concrete section, bending will cause a resultant compressive strength, this, which is a force, FCC, and a resultant tensile strength, which is this, which is also a force. Since these two will act as a couple, these two forces here are a couple, one is acting this way, this one is acting the other direction, they constitute a couple. The moment M can be calculated from, you can get the moment M, you can easily calculate it from this multiplied by lever arm, which is FCCZ multiplied by Z, or Fx, this multiplied by its own lever arm 2, which is Z, where we have these parameters. FCC is resultant concrete force, resultant concrete force. Then we have Fs is resultant steel force. Then we have Z is the lever arm, then FCC, we now get FCC, which is equal to stress in concrete multiplied by the area of concrete, So our stress in concrete, as you can see here, is this multiplied by this. This is the stress in concrete, and the area of concrete, we multiply this depth by the breadth. So we'll have it, our FCC will be equal to 0.45, FCU 0.45, FCU BS and so that is it. That's the force in concrete. And remember that Z is equal to D minus 0.5s. So this Z here, we have this place is supposed to be 0.45 or 0.5s, but it's half of this block. So from here to here is half of this overall depth. When you divide this by 2, you have 0.5s. So S will be equal to D minus Z over. So we have M is equal to 0.45 FCU PS Z multiplied by lever arm, which is Z. Remember that 0.45 FCU was obtained from 0.67 FCU divided by the material strength of 1.5. So we're able to obtain 0.44, which we approximated to 0.45. So we have this, and when we substitute the value of S here, we'll have M equal to 0.45 FCU B in brackets. We have D minus Z over 0.5, close this bracket. Then we have Z outside. This to be equal to, if we expand this divided by this, we're going to have 0.9 FCUB in bracket. We have D minus Z, we have another Z outside. So dividing both sides by, we divide both sides by this side, this, where you have M equal to this. So when we divide both sides by dividing both sides by, let's use FCUB dot times D square. Let's divide both sides by that. We are going to have M over FCU B D square is equal to, the other side will be 0.9 FCU, then we'll have D minus Z outside over FCU BD square. So here we have FCU, here. Remember we have B here. So these will cancel this. So what we have here is, we have M over here. Let me wipe off this so that it will not conflict with what we're doing. So what we have here is, we have M over FCU BD square is equal to, when we simplify this, we're dividing, we are going to have 0.9. What will be remaining here is bracket D minus Z, the Z is still outside, over D square. So if we simplify further, we have M over FCU BD square will be equal to, if we simplify this further, we're going to have 0.9 in brackets. We can expand that, expand this. We're going to have 1 over D. Here we have this and this, so we're going to divide all through by D square. So what are we going to have? 1 over D minus, we have Z over D square, since we're dividing both sides by D squared, and we'll still have our Z outside because we were having D before. So when we divide this by D squared, it will be 1 over D minus Z divided by D squared. We have bracket Z. So this is what, so we say let K equal to this, let K equal to M over FCUBD square. So we're going to replace this with K. So what will we have here is, have K is equal to 0.9 bracket 1 over D minus Z over D squared close the bracket Z. So we expand this. We can say or can divide both sides by 0.9. K can say or K over 0.9 will equal to, here we have, to expand this, we have Z over D minus Z square over D square. So this is still the same thing as K over 0.9 is equal to, here we have Z over D minus, bring this out, Z over D squared. So we have this, and this is still the same thing as, we can take this one to this side, it can be Z over D squared is equal to Z over D minus K over 0.9. So we can still make it Z squared over D is equal to, or minus Z over D plus K over 0.9 is equal to 0. So this looks like a quadratic equation. So comparing it with the general quadratic equation, which has a solution of, we know that general quadratic equation has a solution. This is the formula we use in solving that. We use x is equal to minus b plus minus square root of b square minus 4ac over 2a. So if we do that, we can now solve in this equation using this quadratic equation. We'll obtain, we have Z over D is equal to 0.5 plus square root of 0.25 minus K over 0.9. So this is what we have, or we can say Z is equal to bracket 0.5 plus square root of 0.25 minus K over 0.9 close the bracket D. So here you may be wondering how we're able to get this using this equation. You consider solving, if you can solve quadratic equations using the general formula for quadratic equation, you can be able to solve this considering the coefficient of this very one is 1. Here we have 1 also, minus 1. Here we have K over 0.9 as our C. This one minus 1 is B, and 1 plus 1 is our A. So when you substitute it into this, you'll be able to obtain this. So this is the equation for the determination of the lever arm for a singly reinforced section as stated in the code, and its value is limited to 0.95 D. That is LA is given by, let's clean the board, clean this. So LA is given by our lever arm factor. LA is given by 0.5 plus square root of 0.25 minus k over a. This is k over 0.9, close the bracket, d, and this should be less or equal to 0.95, where L A is equal to Z over D, or Z is equal to LAD. Working with the steel force, we've considered concrete force all along. So working with the steel force, we know that the steel force, which is Fs, is equal to Fy over material strength of steel multiplied by As. So, but our As, here we have, if we're using material strength of 1.05, we'll have our Fs will be equal to Fy over 1.05 As, and this will be equal to 0.95 Fy As. But we know that M is equal to F S Z, that is this multiplied by lever arm of Z, which we have here. So what we have next is, hence, clean this side. Hence we obtain As. We know that we have this already, which is M. So we make As the subject of formula. As will be M, because we already have this. This is our Fs times Z. So what we're going to have is As is equal to M over 0.95 Fyz, and this will still be equal to, if we want to replace Z with LAD, since Z or Z is equal to LAD, we have M over 0.95 Fy LAD. This is the design formula for the calculation. This, what we have here, is the design formula for the calculation of the reinforcement of a single reinforced concrete section in bending. In addition, the maximum depth of the neutral axis allowed by the code is X equal to 0.5D. This gives rise to a minimum Z value of 0.775 D. So substituting this value into the equation for the moment of M, here we have our equation where we derived the moment, we've already wiped it out. We have, let's write it again. We have M is equal to 0.9 FCU B bracket D minus Z. We'll have this. So substituting that, we have for Z, we'll have our M, which will be M subscript U, which is M ultimate moment. Will be 0.9 FCU B. We have our D minus our Z is 0.775 D. Remember, we have Z outside, we omitted this, so we have to multiply again by 0.775 D, and this will be equal to 0.156 FCU BD square. FCU BD square. When the applied moment is greater than the ultimate moment, if the applied moment is greater than the ultimate moment, it means we must provide compression reinforcement. So the next example we're going to look at is for doubly reinforced concrete.